Example 7 and 2.6, using the binomial expansion theorem is what this is called. The problem type, we're going to have a binomial raised to an integer power. And in fact, a whole number power. So second power, third power, fourth power, and so on. It doesn't work if it's to a half power, some fractional power. Negative powers, I suppose, would be on the bottom. Then it'd be a positive power. You can still work it out like that. But here's what you want to do. Your problem type is that you want to pick the row that has one more than the power n. So whatever the power is, let's say it's the fifth power. 1, 2, 3, 4, 5, 6 terms. So the number of terms is one more. Easier way for me to know which row to use is this row matches the power. So that second one over from the ones matches the power. This right here is called Pascal's triangle, attributed to Blaise Pascal, a mathematician from, I believe, the 16th century. It's basically you start off with 1, 1, 1, and ones go down the outside. You get any other number just by adding the 2 above it. So 15 and 25 make 35. 126 and 126 make 252. 1 and 5 make 6, and so on. So just you get the triangle going, and then just take 2 numbers above to get each next one. Keep the ones on the outside. These are the magic numbers that allow us to expand things. And your construction of the terms is you take the Pascal triangle number, the first one. I thought I had an underline. Used to not use this board. First Pascal triangle number, and then you take your first object to the nth power, and you take your second object to the 0 power. All right? And then the next Pascal triangle number, you drop the power of the first one by 1, you raise the power of the second one by 1, and so on and so forth. All right? And then once you've constructed the terms, you simplify each term as much as possible. Okay? This is a shortcut. It's a little complicated for people. I'm going to print this out for you guys so you'll have it. But it's a little complicated, but once you understand it, it's a big time saver. Especially because this structure happens a bunch. Okay, it just happens a bunch, so we want to get used to it. So let's try this out. Expand x plus 3 to the 4th power. So my Pascal's triangle, if I were to draw it out, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And that's the row I want. 1, 4, 6, 4, 1. There we go. So again, in each case, I'm just adding up the numbers above. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 4 is 1. 1's on the outside. And there's my power row right there. 4 is the power we got, so that's the row I want. Okay. So as far as construction of terms is concerned, so I'm picking this row, 1, 4, 6, 4, 1 is my magic numbers. I'm going to make 5 terms. Term 1, I take Pascal triangle number 1, which is 1. My first term here is an x, so I'm going to take x to the 4th power. My second term is a positive 3, so I'm going to take positive 3 to the 0 power. Do pay attention to signs. Okay? In the construction phase, everything's plus, but if one of these numbers is negative, it can create a negative term. Okay? So signs do matter. In this case, everything's plus. You're just going to get a bunch of pluses. All right? Second term, I move to the next Pascal number, which is 4. So plus, next Pascal number, I'm going to take x 1 lesser power, 3 to 1 bigger power. Next Pascal number is 6, so I put plus 6. I take x to 1 lesser power. I take 3 to 1 greater power. Next Pascal number is 4, so I put plus 4. I take x to 1 lesser power, 3 to 1 greater power. And my final Pascal number is 1, so I do plus 1. I take x to 1 lesser power, 3 to 1 greater power. Okay, so again, that's the construction of the terms. Just write it out. Okay, and then simplify if possible. Okay, there's always some 0 powers, so they equal 1. All right. There's also 1s in the Pascal numbers, so there's a bunch of multiplication by 1 happening on some of these. So 1 times x to the 4th times 1 is just x to the 4th. So that term becomes that. I suppose I should use the same color for each term. That might make more sense. Let's go red there. Okay. The next term is blue. Okay. 4 times 3 makes 12. X cubed. Next term green. 9 times 6 is 54. That's x squared. Next is this one, purple. 27 times 4 is 108. And finally, we're back over to orange here. 3 to the 4th is 81 times 1 times 1 is going to be plus 81. And that is x plus 3 to the 4th power. efficiency, time saver. To do it by hand, x plus 3 to the fourth, I would do x plus 3 times x plus 3 times x plus 3 times x plus 3. That's how I would do it. Let me get these black here. More contrasting colors. And then I would do a binomial squared. That's x squared plus 6x plus 9, right? And this other one's also x squared plus 6x plus 9. And then I'd go on the distributive property. This x squared times all three of those. That 6x times all three of those. That 9 times all three of those. Do all those multiplications. So I'm going to get x to the fourth plus 6x cubed plus 9x squared. I'm going to get 6x times all that. So 6x cubed plus 36x squared plus 54x. And then I'm going to get 9 times x squared, 9 times 6x, and 9 times 9. And that gives me x to the fourth plus 12x to the third plus 18 and 36 is 54x squared. 54 and 54 is 108x plus 81. Same result, a lot more to write down. So the efficiency of Pascal's triangle comes with time. As you practice it and get good at it, you can go through this process very rapidly. If it's a very basic thing, then it's even faster than this. I mean, you could probably just construct the term in your head and just write down the simplified form as you go, if you get good enough at it.